Welcome to an introduction to real analysis. We're going to go through section by section, beginning here in Chapter 1, Section 1 with basic properties of the real numbers. Now, in analysis, the main set that we work with, at least at the beginning of our study, is the set of real numbers. Now, this set is so fundamental, and often a lot of time is spent just to formally construct what the set of real numbers is. But we're going to take, a more direct approach and assume that a set exists with the relevant properties. The three properties that we need the real numbers to have is that it is an ordered set, it is complete with respect to this order, and it's a field. And we're going to define all of these terms presently. So first, let's talk about what it means to be an ordered set. So an ordered set is a set with a relation, and we're going to use this less than symbol, so that if you pick any two elements of the set, exactly one of the following holds. X is less than y, x happens to be the same element as y, or y is less than x. So an ordered set, if you take two elements out of the set, if they were the same element, great, they're equal to each other. If they're not the same element, then one of them is less than the other. Furthermore, this relation needs to be transitive. If x is less than y and y is less than z, then x must be less than z. So an ordered set has this ordering, and we use the less than symbol. It has to be transitive, and it has to have this first bullet point is often called the trichotomy property. If you pick two elements out of the set, either the first is less than the second is less than the first, or they were the same element to begin with. This is all it means to be an ordered set. Once you've defined this relation, which we used less than, you can define bigger than, less than or equal to, bigger than or equal to, all in the standard way. We're really not going to spend time discussing that. So what are some examples of ordered sets? Now, rational numbers, Q, that's an ordered set. We say that one rational number x is less than y if and only if y minus x is a positive rational number. And by definition, positive rational numbers are those p over q, where p and q are both natural numbers. Similarly, the natural numbers and the integers can be ordered in the typical way. There are other ordered sets other than sets of numbers. So for example, you could talk about the set of countries and order them by land mass. So India is a larger company than Liechtenstein, so India is bigger than Liechtenstein. This is just placing an ordering on a set. Another typical ordering that many people have experience with is the dictionary. It uses what's called the lexicographic ordering. In other words, A comes before B and B comes before C and so forth. And if two words share the same first letter, you can assign an ordering based on the second letter. And if they share the first two letters, they can be assigned an ordering based on the third letter and so forth. Ordered sets appear often in computer science, for example. Now, in this text, and in this series of lectures, we're really just going to be concerned about ordered sets of numbers. All right, now we're going to talk about bounds, suprema, and infima. So suppose that S is an ordered set. So it has an ordering on it. For us, this is typically just going to be real numbers. Okay, the definitions extend in generality, but there's no harm right now for assuming we're talking about ordered sets of real numbers. E is a subset. So E is a subset of the real numbers. That's typically how we're going to work with it. Now, assume that you have B an element of S. Note that B is not an element of E, it's an element of the ordered set. So typically this is just going to be a real number. However, for every element of the set, that element is less than or equal to B. So in our scenario, where we're just talking about numbers, we have a real number, and everything in the set is less than or equal to that number. Then we're going to say that the set is bounded above by this number b. This number b is called an upper bound of the set. Furthermore, if we assume that anything that happens to be an upper bound is bigger than or equal to b, so b is an upper bound, but any upper bound is at least that big, then we say that b is the least upper bound of the set. So of all of the upper bounds, it's the smallest, and this is called the supremum. It's an upper bound, and it's the smallest possible upper bound. If you state all of this with the inequalities reversed, then you can talk about E being bounded below, a number being a lower bound of a set, and if it's the largest of all possible lower bounds, that's called the infimum of a set. If a set is bounded both above and below, we call the set bounded. Now, I want to stress that all of these definitions have been smushed into one slide, but it's really foundational to get your heads around this. This is where the entire field is going to start. Okay, so a set, and again, for now, we can just talk about numbers. A set of numbers is called bounded above if every element of the set is less than or equal to some fixed number. If of all of the upper bounds you have found the smallest possible one, that's called the supremum of a set. If everything in the set is bigger than or equal to a particular number, then you would say that that number is a lower bound. And if all possible lower bounds, if you found the largest one, that's called the infimum. So now let's talk about a few examples. Consider the set just 1, 2, 3, 4, 5. Okay, so we just have 5 numbers. And we're going to order them as expected. 1 is less than 2, 2 is less than 3, 3 is less than 4, 4 is less than 5. Now consider the subset 2, 3. Now this set is bounded above by 3. Everything in the set is less than or equal to 3. 2 is less than 3, and 3 is equal to it. However, the set is also bounded above by 4 and 5. 2 and 3 are both less than or equal to 4, and they're both less than or equal to 5. Observe, however, that in this particular example, we can't say that 6 is an upper bound because our entire universe is just the numbers 1 through 5, so 6 isn't even up for discussion. If we were just talking about numbers, sure, this set E is bounded above by 6 and 6.2, etc. Now 3 is an upper bound of this set, but in the entire universe of discussion, the only possible upper bounds are 3, 4, and 5. So of all of the upper bounds of this set, 3, 4, and 5, the smallest one is 3. So we have found the smallest possible upper bound. In other words, 3 is the supremum of E. Similarly, this set E, which contains only 2 and 3, is bounded below by both 1 and 2. 2 is the greatest of all the possible lower bounds, therefore it is called the infimum. This set E is bounded above and below, so it is therefore bounded. Suppose we have the set of rational numbers, again with typical ordering that we're all used to. Let's let E be the set of rational numbers which are less than 1. Now, by definition, we see that 1 is an upper bound of E. Everything in the set is less than 1. But in fact, 1 is the supremum. Anything that is bigger than all rational numbers less than 1 must itself be at least 1. Okay, we're not going to go through the proof of this, but if all rationals less than 1 are less than some number, that number cannot also be less than 1. So 1 is not an element of the set E, but it is, of all possible upper bounds, the smallest one. In other words, this set has a supremum. Its supremum is 1. 1 is an upper bound, and it's the smallest possible upper bound, but it's not actually in the set. So it's entirely possible for a set to have a supremum, and the supremum may not actually be in the set under consideration. Also, this set E doesn't even have a lower bound. We were taking here all rational numbers less than 1. That goes off for larger and larger negative numbers. Those would all be less than 1. So there is no lower bound to this set. We would therefore say the set is unbounded or not bounded below. Okay, here's the next major definition, completeness. An ordered set is called complete, also called Dedekind complete, or having the least upper bound property, but in modern parlance, complete is the term that you'll always see. A set is called complete if every non-empty set that has an upper bound must have a supremum. So this is just a property that a set can have. Any set that has any upper bounds at all must have a smallest possible upper bound. What does this definition do for us? Well, observe, for example, that the rational numbers do not have this property. So this is very much a non-trivial property to assign to a set. So suppose you have your typical ordering of the rationals, and now consider the set of rational numbers whose square is less than 2. Now 2 is an upper bound of E. Okay, if you have a rational number whose square is less than 2, first of all, if the number was less than or equal to 0, it's definitely less than 2. If the number was positive, then since any number bigger than 2 would square to be at least 4, any number whose square is less than 2, the original number must have been less than 2. Okay, so 2 is definitely an upper bound. The set of rational numbers whose square is less than 2 doesn't contain anything bigger than 2. But there is not, in fact, a least upper bound of this set. So sure, anything that squares to be bigger than 2 would be less than 2, but it would also be less than 1.9, and it would also be less than 1.5, but not necessarily less than 1.4. So suppose you have a rational number whose square is less than 2. It is always possible to find a larger rational number whose square is still less than 2. We're not going to work through the proof of this. It's a little tedious, but if you have a rational number whose square is not quite 2, you could have started with something very, very slightly larger and still have a square less than 2. So no number whose square is less than 2 is an upper bound of E. That actually tells us that no element of E can be an upper bound of E. But now consider something whose square is larger than 2. You can still find something smaller whose square is larger than 2. And again, we're not going to work through the proof here. But if you have something whose square is, for example, 9, like 3, then you could have had something a little bit less, 2.9. The square would still be larger than 2. Any rational number whose square is larger than 2, something a little bit smaller would still have a square less than 2. So if something squares to less than 2, it's not an upper bound of E. But if something squares to be bigger than 2, it couldn't have been the smallest upper bound of E because something a little bit smaller would still have this property. So anything whose square is less than 2 cannot be the supremum because it's not even an upper bound. Anything whose square is bigger than 2 can't be the supremum because even if it were an upper bound, it wouldn't be the smallest one. We also leave out a proof of the classical fact that there is no rational number whose square is equal to 2. So what do we have? Anything whose square is less than 2 cannot be the supremum. Anything whose square is bigger than 2 cannot be the supremum. And there isn't a rational number at all whose square is equal to 2. Therefore, there is no rational number that is a supremum of this set E. So the rational numbers are not complete. This set E is bounded above, but does not have a supremum. Now, this completeness property really is crucial for doing the field of analysis. The rationals don't have this least upper bound property or completeness, and that's pretty much why we don't do analysis in the rational numbers. We work in the reals, which we will shortly see are complete. Now, the rational numbers have a lot of very nice algebraic properties, and we need more. We need this completeness property to do analysis. So we're not just going to work in the rationals. We do still need these algebraic properties. Specifically, the set of numbers in which we're going to operate, we really want them to be what's called a field. So what is a field? A field is a set that has two operations, which we're going to denote addition and multiplication. So the set has to be closed under these operations. Any two elements of f, you can add them or multiply them and still be an f. These two operations are commutative and associative. In other words, order of operations strictly between addition or multiplication doesn't matter, and left versus right doesn't matter. Also, there's an additive identity and a multiplicative identity denoted respectively as 0 and 1. So 0 is something in f that when you add it to something doesn't change it, and 1 is something that when you multiply by it doesn't change it. Furthermore, for any element of f, there has to be something that you can add to it to get out 0. So there have to be inverses under addition, which we denote as negative x. Similarly, if you didn't start with 0, there has to be a multiplicative inverse, something that you multiply it by to get out 1, which we denote as 1 over x or x to the minus 1 power. And finally, these two operations of addition and multiplication have to interact according to a distributive property. X times y plus z is always going to be equal to x times y plus x times z. And all of these things we are all totally used to doing with real numbers. You can add real numbers, you can multiply them. Those operations are commutative and associative. Adding 0 doesn't do anything, multiplying by 1 doesn't do anything. Furthermore, you can have negative numbers that add to 0. You can have 1 over something to multiply it to get out 1, as long as you don't have a 1 over 0. And the distributive property holds. So none of this is a big surprise for any student in this course. This is what it means to be a field. So here's an example. The rational numbers, while they are not complete, they are a field. The set of integers, however, are not. So the integers, with addition and multiplication defined as, we always do, satisfy all of these conditions except there are not necessarily multiplicative inverses in the integers. For example, 2 is an integer, but there is no integer that you can multiply by 2 to get out 1. I'm not saying there isn't a number, it's just not an integer. So the set of integers is not a field. It is a ring, but that's a whole separate thing. Also note that if we set z equals 0, the final distributive property here, x times y plus z equals x times y plus x times z, well, if z is 0, we already know that y plus z must be y, so this gives us x times y equals x times y plus x times z, and you can prove that 0 is the only thing that when you add does nothing. Therefore, x times z must be 0. So that's a short little thing that you can do to show that 0 is the additive identity. Adding 0 does nothing. The distributive property forces it to have this property that 0 times anything must be 0. And now we get to our next definition, an ordered field. Suppose you have a field, so it has addition and multiplication with all the standard properties that we're used to doing. Also, it's ordered according to this symbol less than. We're going to call that thing together an ordered field if two things hold. First, if x is less than y, then x plus z must be less than y plus z. In other words, you can add things to inequalities quite freely. Furthermore, if x and y are both bigger than 0, then x times y must be bigger than 0. If both of these things hold, you call it an ordered field. Then you can define the terms positive and negative to be something bigger than 0 is positive and something less than 0 is negative. And again, the real numbers, which is what we're going to be working with, have these properties. So, proposition 1.1.8. Suppose f is an ordered field and you pick 4 arbitrary elements out of it. First, if x is positive, then its additive inverse, negative x, must be negative, and vice versa. If x is positive and y is less than z, then you can multiply an inequality. So while you can always, by definition, the first bullet point in the definition, you can always add to an inequality. You can multiply by an inequality freely as long as you multiply by a positive number. If, however, you have a negative number and you multiply an inequality, it will reverse the direction of the inequality. If x is anything other than 0, so anything other than the additive identity, when you square it, you will get a positive number. If x is in between 0 and y, then reciprocation, or taking multiplicative inverses, reverses that inequality. And if x is in between 0 and y, then squaring will preserve that inequality. X squared will be less than y squared. Finally, 7, if x is less than or equal to y and z is less than or equal to w, then you can add them. So you can add two inequalities together as long as you're adding them in the correct direction, by which I mean x was less than or equal to y, z was less than or equal to w, so left plus left is still less than or equal to right plus right. And we're not going to prove these things. It's really an algebra exercise, not an analysis exercise. The book itself has proofs for about half of them. Next, proposition 1.1.9, suppose you have an ordered field, you pick two elements of it. This is useful if two things multiply together to be positive, then either they were both positive or they were both negative. And we'll prove this. So we've already remarked that anything times 0 must be 0. So if the product of two things is bigger than 0, neither one of them was 0 to start with. Okay. Suppose that you don't have what we want. We want to show either they're both positive or they're both negative. So suppose to the contrary that one of them is positive and one of them is negative. Now, y less than 0 is an inequality that we have just assumed that we can work with. But we also know you can multiply inequalities by positive numbers. So multiply by the positive number x. This gives us x times y less than x times 0. But what is x times 0? It's 0. But we assumed at the very beginning that x times y is bigger than 0, so here we have a contradiction. Because remember, in an ordered field, if you pick two things, either one is less than the other, or bigger than it, or equal to it, but it cannot be both. So since we've assumed that x times y is bigger than 0, it can't simultaneously be less than 0. Here's another example. The complex numbers, they are a field. It has all of those properties of addition and multiplication doing all the nice things. You also can place an order on them. It is totally possible to order the complex numbers. What you can't do, however, is make an ordered field out of it. Remember, an ordered field had to have a couple extra conditions, not just be a field with an order. So we observed before that for any non-zero element of an ordered field, the square has to be positive. 0 must also be in between 1 and negative 1. Okay, 1 has to be positive essentially by definition. You pick it to be positive or negative, and then its additive inverse will be the opposite. We just declare the positive 1 to be 1 and the negative 1 to be minus 1. But in the complex numbers, remember you have this element I whose square is negative 1, which is less than 0. So anything squared has to be bigger than 0, but I squared is less than 0. Therefore, it can't be an ordered field. The complex numbers are absolutely a field. They absolutely have orders that you can place on them. It just won't interact together nicely to make what we have defined as an ordered field. So how come we defined all of this stuff for the completeness property in terms of upper bounds, but we didn't do the same thing for lower bounds? What we'll see shortly is that if you have an ordered field, then the assumption of completeness, which by definition only interacted with upper bounds and supremums, will automatically imply the same condition for lower bounds and infima. So next, proposition 1111. Suppose you have an ordered field which is complete. If it's bounded below, it must have an infimum. Now, as pointed out in the upper right, this definition of completeness, if a set is bounded above, it must have a supremum. What we're proving now is that the opposite must hold. If it's bounded below, it must have an infimum. So starting with this set A, which is bounded below, we're going to define the set B to be the additive inverses of everything in A. So take everything in A and just take their negatives. Note, if x is negative, then negative x is positive, whatever. Whatever the elements of A are, we're just taking their negatives. Well, the set A was assumed to be bounded below, so it has a lower bound. Let's let that lower bound be called B. So for every element of A, B is less than or equal to x. Everything in A is bigger than or equal to B. The set A is bounded below by B. But now if I multiply this by negative 1, we flip the direction of the inequality, and therefore negative B is bigger than or equal to negative x for every element of A. But if I take every element of A and I replace it with its negative, that just gives me the set B. In other words, this number is an upper bound of B. So this set B is bounded above. It's bounded above by the number negative little b. But we assumed that our ordered field is complete. So since we now have a set which is bounded above, specifically the set B is bounded above in a complete ordered field, so it must have a supremum. Okay, so this set B has to have a supremum. We're going to call its supremum lowercase c. Now the set capital B was just the negatives of the original set A. So since this number c is the supremum of B, it's an upper bound. Everything in B is less than or equal to c. But if I multiply again by minus 1, negative y is bigger than or equal to negative c. But if I take negative 1 times the elements of B, I go back to elements of A, meaning every element of A is bigger than or equal to this number, negative c. All that does is tell us that negative c is a lower bound of the set A. That doesn't seem like a whole lot because our original assumption was that the set A is bounded below. So what have we actually done? We began with our set A, which is bounded below. We just know that it has a lower bound. That correspondingly gave us an upper bound on the negatives, and the set of negatives we called B. But therefore, this number is an upper bound of B, which means it has to be bigger than or equal to the supremum, because the supremum of the set is an upper bound, but it's less than or equal to any other upper bound. So since this number is an upper bound of B, the supremum is less than or equal to it. So C is less than or equal to minus B. In other words, B is less than or equal to minus C. So negative C is a lower bound of A, but any arbitrary lower bound of A is less than or equal to that. So this number is a lower bound, but an arbitrary lower bound is less than or equal, meaning of all lower bounds, this thing right here is the biggest possible one. By definition, it is the infimum. So a roundabout proof, by multiplying by -1 twice, essentially, that if a set is bounded below, it must have an infimum, assuming we're working in a complete ordered field, which only made assumptions about supremums existing. This is basically just justifying that the original definition of completeness doesn't make reference to infima. Once you make an assumption that supremums have to exist for sets that are bounded above, in ordered fields, this will automatically give you that sets which are bounded below must have infima. It might seem like less work to just throw that into the definition of completeness, and it would be, but we place a lot of value and emphasis on not defining things when you can improve them instead. So in review, all we really did was lay a foundation for everything we're going to do from this point forward. We're going to be working in the real numbers R. What properties do the real numbers have that are going to be important? Exactly the definitions that we've laid out here. We want an ordered field that is complete, and we're going to see in the next section that the real numbers have this property. In fact, that's basically how we're going to define the real numbers.